The word eclipse is from the Greek eclipsis, which means abandonment. And the sun is such an essential part of human existence. We wouldn't be here, let alone survive, were it not for the sun. So when it abandons us in a surprising way, it has a dramatic effect. And I personally very fond of these two historic anecdotes. In 580s BC, Herodotus reports that a war between the Lydians and the Medes was ended by a solar eclipse that took both armies by surprise during a battle. Apparently what happened is the battle was enjoined and the sun was suddenly eclipsed, and the kings of both tribes felt that it was the god's anger that had produced the eclipse, and so they had themselves a marriage, the son and the daughter and whatever, in order to appease the gods. In 1504, Christopher Columbus convinced Jamaicans to aid him by threatening that the Christian God would swallow up the sun in anger, an event which then proceeded right on schedule. I think it's remarkable. We talk about, Columbus proved that the earth was round. Certainly he did not. He knew very well that the earth was spherical. It was his intent to sail around, to get to the east by sailing around the other way, by going west. And he had remarkable mathematical abilities and was able to predict a solar eclipse at a latitude and longitude other than his home latitude and longitude. It's a remarkable achievement, and it lends itself to an understanding that Christopher Columbus had a high level of mathematical sophistication, as he would have to pull off the navigational feats involved in discovering the New World. Eclipses occur because of shadows, and here I'm looking at the geometry associated with a lunar eclipse when the moon temporarily disappears. The reason why this happens, I think is generally known, is that the moon enters the shadow of the Earth. The moon is only lit up in the first place because it reflects the light of the sun, and when the Earth gets in the way, the shadow of the Earth is projected onto the moon. Now, this diagram shown here is not to scale. I'll remind you once again that if the Earth is the size of my fist, then the moon is the size of my thumb 3 meters away. Nevertheless, it is true that the moon fits well within the shadow of the Earth. And so if the sun, the Earth, and the moon get lined up properly, then the moon can be within the shadow of the Earth and not reflect the sunlight. Notice that in this configuration, if you're standing on the surface of the Earth and viewing the moon, you would expect a full moon. Because when the moon is in this position relative to the sun, that's when we expect the full moon phase to take place. An interesting thing here as well is that there are two aspects to the Earth's shadow. One is the shadow in which the moon is currently located in this diagram is called the umbral shadow, the complete darkest shadow of the Earth. But above and below, we have the penumbra shadow, where part of the light from one side of the sun is able to reach that point, where the light from the other side of the sun is not. We get partial illumination. So what we see here is the Earth's shadow and the moon passing through it. There are occasions when, as in the moon in the center configuration, where the moon travels entirely through the umbral shadow. This is a total eclipse of the moon. It gets entirely inside of the umbral shadow. The lower version is when the moon passes partially through the umbral shadow and partially through the penumbral shadow. As a result, we see a partial eclipse. And of course, there are other situations where the moon passes, as in the top case, only through the penumbral shadow, and we call this a penumbral eclipse. A total eclipse of the sun occurs when the shadow of the moon is cast upon the Earth. You can see from this diagram, once again, horribly not to scale, that the situation geometrically is quite different. The shadow of the moon cast upon the Earth is quite small. If it were larger, such that the Earth could fit entirely inside the moon's shadow, you would expect that you'd be able to see a total eclipse of the sun from everywhere on the surface of the Earth simultaneously. But it turns out, as you might expect, that when a total eclipse of the sun happens, it only happens on certain very limited areas on the surface of the Earth. This is because the shadow of the moon on the surface of the Earth is quite small. The nomenclature is the same, however. The moon has an umbral shadow and a penumbral shadow just as the Earth does. When it comes to the frequency of lunar and solar eclipses, we look to the geometry of the Earth and Moon orbit in order to see when such things are favorable. You might imagine that every time there's a new moon, you would expect that there would be a total eclipse of the sun, because a new moon takes place when the moon is between the sun and the Earth. But it turns out that the orbit of the moon around the sun is inclined at 5 degrees relative to the plane of the orbit of the Earth. This means that there are only 2 points in the moon's orbit where it actually intersects with the plane of the Earth's orbit. In one case, it is rising from below the Earth's orbit to above it. We call this the ascending node. And on the other side, it is going from above the Earth's orbital plane to below it. We call this the descending node. At the ascending and descending nodes are the only 2 points in the orbit of the moon around the Earth when the Earth and the moon can truly line up. So here we have the situation looking from the side, where we see the light from the sun, which is off to the left in the uppermost part of the diagram. Light from the sun is parallel rays coming from the left, and the moon shown both in the new moon position, when it's in fact between the Earth and the sun, and in the full moon position, when it's opposite the Earth and the sun. Again, this diagram is not to scale. The situation is far worse than it looks. But we can see in this configuration that the moon's shadow will not fall upon the Earth, and that the shadow of the Earth will not fall upon the moon. So when the Earth and the moon are in this configuration, where the moon is either a bit above or a bit below the plane of the Earth's orbit, this is a situation unfavorable to eclipses. Just below, we see the Earth and the moon in such a situation that the moon is either at the descending or the ascending node. At the new moon, its shadow would be projected upon the Earth, and we can see a solar eclipse. With the full moon would be entirely within the Earth's shadow, and then we would see a full eclipse of the moon, or a total eclipse of the moon. We see in the bottom half of the diagram this situation in 3 dimensions. As the Earth orbits around the sun, the plane of the moon's orbit goes along with it. So there's a time during the year when we are favorable for eclipses and a time during the year when eclipses are unfavorable due to the inclination of the moon's orbit relative to the Earth's orbit. Here are a few consequences of this. If you do the mathematics of the thing and work it out, the moon and the sun have roughly the same angular size. This is why we get total eclipses of the sun. When we see a total eclipse of the sun, the disk of the moon has to completely obscure the disk of the sun. And it just turns out, coincidentally, that here on Earth we have that sort of geometry. I've often mused that if there ever is a sort of galactic community, that the Earth might be a bit of a tourist attraction because we have this special feature that eclipses of the sun are so spectacular because of how similar in angular size the disk of the sun and the disk of the moon are. It's complete coincidence. Lunar eclipses last about an hour and 45 minutes. And they happen quite often, so you'll hear about them in the news or through this course or through your own research and have an opportunity to make a cocktail and go out on the lawn and join the neighbors and watch the eclipse take place in short order. The moon's umbral shadow on the Earth, however, is only about 167 miles wide. Thus, solar eclipses last no more than 7 minutes and 30 seconds. So you have to be prepared for that because it's going to be a relatively short event. If I ask a question at this point for you to calculate for your own interest. If the moon's shadow is 167 miles wide and solar eclipses only last 7 minutes and 30 seconds, how fast is the moon's shadow traveling across the surface of the Earth? See if you can calculate that. Total eclipses occur every 18 years and 11 days. So total eclipses of the sun are actually quite frequent. But the thing is that on average, on a given location on the surface of the Earth, you can only see a lunar eclipse You can see a lunar eclipse just about every year and a partial every other year, but a total solar eclipse happens only about once every 400 years at any given location on the surface of the Earth. And in fact, there was a situation where a total eclipse was happening in Chile, and it was going to occur as the sun set over the Pacific Ocean. And it occurred to me to fly to Chile to sit on the beach and watch it happen. And then I found out how much the flight would cost, and that changed my plans. And it was lucky that that happened, because it turned out that the weather was cloudy and the eclipse couldn't be seen. There's going to be an eclipse, I believe, in 2012 in St. Louis in the United States. Will be the best place to view that. So we can all travel there and enjoy what St. Louis has to offer and observe the eclipse at that time. Also, we have this things going on with the Mayan calendar and the prediction that the world's going to end in 2012. There's a feature-length film that's about to come out as of the recording of this lecture. About 2012 being a fascinating time. None of that has any scientific legitimacy, and you should research into that. Nevertheless, total solar eclipse in our area. I don't know when the last time it happened in Philadelphia, but you have to wait 400 years to see the next one if you're unwilling to travel to see a total eclipse of the sun. Here is a partial lunar eclipse, and we see the reddish colors due to diffraction effects of the sunlight bending around the Earth. Here's the sun partially obscured. We see the shadow of the Earth projected. I'm sorry, this is the moon partially obscured. We see the shadow of the Earth projected onto the moon. This naturally is a total eclipse of the sun. We see just at the top of the photo the sunlight eking over the edge of the moon. This is because the angular sizes are so close. You can see at the bottom actually a little bit of brightness as well. That's how close they are to being the same angular size. This brightness that we see around the outside is the corona of the sun, which normally we don't see because the surface of the sun itself is much, much greater in intensity. Nevertheless, this coronal discharge of the sun is what burns your eyes if you look at a total solar eclipse. Looking at a total eclipse of the sun you're no better off than looking at the sun itself. Naturally, we learn very early age not to look at the sun. Similarly, we should not look directly at solar eclipses because of the potential for damage of our eyes. Here is the sun passing very nearly, but not quite completely, or the moon, not completely obscuring the disk, and we get this bright flash. This is often called the engagement ring eclipse. Here is an image taken by satellite of the shadow of the moon projected on the Earth. Naturally, it's not a solid with a distinct edge, but you can see it's sort of spans the Gulf of California here, and it's about 167 miles in diameter, but it travels across the surface of the Earth, and only if you happen to be standing in that shadow do you see the total eclipse of the sun. I wish I had this diagram for North America, but England will do. Here we see, well, Great Britain, all of Scotland and Wales and Ireland, and we see the regions of totality. In southern England, apparently when this eclipse took place, and I don't know what year it happened, but totality, 100% solar eclipse, only happened in the southernmost tip of England. And you see from southern England to northern England, we only get about, and the furthermost northern Scotland, I suppose, is 75% eclipse. And so all of England would see this eclipse to some extent, but in order to see totality, you would have to be all the way down in Plymouth in the southernmost tip. Here's an image, sequential image of an eclipse. I don't know where this was taken. I imagine it was in South America. But here we see the moon's disk in front of the sun, and yet the sun is not completely obscured by the disk of the moon. We call this an annular eclipse because the sun appears as an annulus at totality. Why should this be the case? What's happening here is that the angular size of the moon appears smaller than the angular size of the sun. The angular size of the sun would be larger if the Earth was closer to the sun. So I imagine this eclipse happened in wintertime also. The annular eclipse is more likely when the moon is closer to the Earth. It also happens to be true that in its orbit around the Earth, the moon gets closer to and further away from the Earth, thus changing its angular size. And so we can have this situation where both are taking place and we get an annular eclipse. This is just for fun. It's another sequential solar eclipse event taking place, one right after the other. And certainly these make for beautiful photographic opportunities. And whenever a total solar eclipse happens, people come out to see it. And I did when there was a nearly total solar eclipse when I was an undergraduate. And I was a member of the Physics Society, and we all, in preparation, made our little pinhole cameras and devices for observing the eclipse as it took place. In the courtyard where we chose to do this, there was a tree, and the tree has leaves, naturally, that overlap. And where the leaves of the tree overlap, you get these little gaps, and some of them the scale of pinholes. And we discovered that despite our best efforts with tinfoil and cardboard and tape and glue to make apparatuses for observing the eclipse, that when the eclipse finally took place, we were showered all around us with little itty-bitty images of the eclipse because all of the overlapping leaves acted as pinhole cameras and created these images as seen here. The leaves of the tree project individual images of an eclipse taking place. Certainly what you should do is to be aware of when eclipses are going to take place, make preparations, take the young ones outside, and enjoy the wonder of this nature, of shadows and the geometry of the orbits of the sun, the moon, and the earth.